And so if you take those two and you bond them together, you now have cyclopentane, and you relieve that interaction by just enforcing it. There's angle strain and ring strain present in cyclopentane. But now you could have a gauche plus here and a gauche minus there, and it doesn't matter because these two are connected to each other. And the idea is sometimes in chemistry we can enforce an unfavorable conformation with a cyclic constraint. You use chemistry to pay the energetic cost of having things in a conformation that wouldn't normally happen. All right. Anything else you want to ask about that? Another kind of strain that's sort of related involves what happens when you put groups adjacent to double bonds. So let's just imagine a pi bond here, carbon 1, 2, 3, and then let's suppose carbon 3 has something on it, something that's not hydrogen. Oops. You might imagine that that could have steric consequences as the proton, the vinyl proton from carbon 1 smashes into protons from the sp3 hybridized carbon that was attached to carbon 3. And of course, I've drawn this in probably not the most stable conformation, because you could rotate around carbons 2 and 3 and bring this alkyl group over here. But the point is that if you have a double bond, there is a chance for steric clash between the substituents on carbon 3 and the proton that's on carbon 1. And this is called allylic strain. Sometimes it's called A13 strain. And this is something that is easy to forget about. And it's an easy question for like an OChem professor to ask you in your annual review or your proposal defense. Or, oh, well, you've drawn this, and what kind of strain, have you thought about what kind of strain is that's there? And then you will feel like, oh, I knew that at some point and I forgot it, and then they'll remind you. So just be aware of that and prepared for it. It actually has an important role in some research problems that people are working on in the department. So Professor Castle's lab published a paper in Orglet a couple years ago in which, let's see, this was like 2017, I forget. If you want to go look it up, you can just Google it. But Professor Castle's lab is interested in a class of amino acids that are called dihydroamino acids. And the reason they're called that is because they have a double bond between the alpha carbon of the amino acid and the beta carbon. And in particular, Professor Castle's group is interested in bulky dihydroamino acids. And they're interested in them because they believe they can restrict the conformational freedom of nearby let's see. Maybe that's not what I want to say. These dihydroamino acids are predisposed to certain conformations. If you notice in this amino acid, there are a couple of bonds that chemists are interested in for details of peptide and protein structure. There's this bond between the nitrogen and the alpha carbon, and then a bond between the alpha carbon and the carbonyl carbon. Those dihedral angles at those bonds are influenced by the presence of these bulky groups here. And this is an example of allylic strain, A13 strain, because the group on carbon 1 is bumping into let's see. No, I got that. Sorry about that. I think in terms of, we haven't talked about this, but the nitrogen is maybe conjugated to the double bond, and so this is maybe the first position of our allyl group. So the substituent on carbon 3 can smash into the groups on carbon 1, like the proton or like this other group. And that steric clash between those two groups restricts the freedom that these amino acids have. I didn't really explain that very well.
Okay. Sorry. Why is it called 1,3? Because the interaction is between 4.
Yeah. Why is it called 1,3? Because if you really look, the interactions between a group on 1 and a group on 4.
Yeah.
I don't know. That's always tripped me up. Because some jerk in the past called it that, and we've all stuck with it. So I think it has to do with the perspective that if you're thinking about building a molecule and you start here and you think, oh, I want to put something there on carbon 3, oh, that could then be a steric clash with something that was on carbon 1. So I think that's maybe why it's not that great of an explanation, and you're right, I think there'd be a better way to talk about it, but there we are.
So the whole idea is that because of the double bond, the bond between 1 and 3 are kind of close. So any substituent that is coming upon 3 might interact with 1. Is that the whole idea?
Yes, I mean it has to do. You're absolutely right. Double bonds are shorter than single bonds. Also, rotation around double bonds is restricted, right?
Okay.
You can't rotate without breaking the pi bond. So this carbon is forced to be sp2 hybridized, as is this carbon, and so that makes it so that whatever's here and whatever's here have to be close to each other.
So the position of the double bond doesn't necessarily have to be between 1 and 2. It could be between 2 and 3. Because
I think so. What matters is that you have an allyl system.
okay.
Yeah. And this doesn't look necessarily like an allyl system, but because that nitrogen would be conjugated to this bond, that's sort of where it is. I suppose, I'm not even sure I'm getting this right, but you could think of it here, 1, 2, 3, this hydrogen bumping into that substituent. Either way, it's A13 strain. There's no convention for which should be 1 and which should be 3. So if you're interested, go and look at that. Professor Castle has shown that if you incorporate this amino acid at a specific position in a peptide, the restricted freedom about these two bonds biases that peptide to form what's called a beta turn, in which elongating chain turns back on itself. He's also shown that if you incorporate these amino acids into peptides, the restricted freedom about these two bonds actually makes it harder for proteases to chew up those peptides, and he's interested in applying that to drug development. Okay. Other questions about that? Yeah.
Sorry, just to go back for a second, but with the pentane, when you
Yeah.
like make it a ring, what were the kind of strains it had? Angle and what was the other one?
So we'll talk about this, but rings have angle strain. And did I say something
I
else?
thought you said something else, but maybe.
I probably said ring strain, but I guess those are the same thing. Okay. And actually, that's exactly where we're going. I want to just see whether. Just want to zoom in on this table. Yeah, go ahead, frantically try to copy everything down. Samantha's not laughing at that one. I'm sorry. Okay, so yeah, maybe we'll start without that. I was going to show you a table of ring strains, but the idea, as we talked about with cyclopropane, is that when you make something into a three-membered ring, the bond angle has to be something different than is preferred for an sp3 hybridized carbon. Now, we've dealt with that with cyclopropane. Nevertheless, you can calculate, being creative with bond dissociation enthalpies, you can calculate the amount of strain that's present in this ring that would not be present in a linear precursor. And if you do that, you get something that's called a strain energy. And for cyclopropane, it's like 27.5 kilocalories per mole. We don't memorize numbers really, so that's not a number that's worth knowing. But the trends are worth knowing and can be useful. There's nothing really that cyclopropane can do to relieve this strain energy. However, the other size rings can. So if you think about cyclobutane, and if you think about if it were completely flat, the bond angles would have to be 90 degrees, right? And that's also distorted from planarity. That's also tighter than you would want it to be. There we go. So what cyclobutane does instead is it adopts a puckered conformation. What do we mean by that? Well, instead of being completely planar, with all of the CH bonds eclipsed and all of the carbon-carbon bonds eclipsed. I haven't drawn the hydrogens in the back because it's hard. Guess we'll still do that. Instead, it relaxes a bit, and the carbons on either end sort of pucker downward, and the carbons in the middle pucker upward. And this relieves some of the strain of the ring, and also because the bond angles don't have to be quite 90 degrees, it also relieves some of the torsional strain between the hydrogens because they're no longer eclipsed with each other. Do you see how if this were a completely flat group, all the hydrogens would be eclipsed? And that's bad. We call that torsional strain. Or that's what we have been talking about with butane and pentane. So you can relieve that a little bit, and you can relieve some of the angle strain by distorting its conformation. So we can maybe draw cyclobutane and see what Spartan comes up with. I haven't done this actually, so I'm not sure what it's going to tell us. Just try. This doesn't do any calculations, it just accesses a database that has previously performed calculations. Okay. Oh, and it's already adopted the pucker. So do you see how that's not totally flat? And if you look down the carbon-carbon bonds, we're not eclipsed anymore. We're not perfect gauche because you can't be in a four-membered ring, but it's better than eclipsed. So yeah, cyclobutane adopts this conformation. It would be flexible. It would be like a little wing flapping up and down probably with time. But it does this to avoid the planar structure. Yeah, go ahead.
Does it just like naturally do this, adopt this puckering shape?
Yeah.
So
Yeah.
it's never ever, hardly ever in the 90 degree.
Well, if you could think about the planar structure maybe being a high energy transition state.
Okay.
Another, I guess, resource that I have that maybe we're instead of showing you static pictures, no, that's not what I wanted, of molecules, this gives you basically molecular dynamics simulations of what the molecules look like in real time. So here, well, real time meaning really, really slowed down time. One of our seconds here is 120 femtoseconds in the molecule's time. So this would be happening really fast. And we can control the kinetic energy of the molecule, which can sometimes change its shape. you can see that at 50 Kelvin, it's pretty well in that puckered conformation with carbon-hydrogen bonds wiggling a little bit. If we turn up the bath temperature, we may be able to see it start to shift from one pucker to another. It's hard to tell because now it's moving around like crazy. Another thing we can do is turn down the temperature and try to make it switch from one puckered form to another just by grabbing a hydrogen and pulling. And it looks like it's pretty easy to do that. Cyclobutane conformations are not going to be like chair conformations where you have one that's a minimum and then another that's not. Probably this switches back and forth pretty easily. But I like this app because you can get a sense for what those barriers are. Notice if I move one of these, it'll adjust itself a little bit, and then you can see groups start to move a little bit, but then go back to their equilibrating conformation. All right. Strain energy for cyclobutane is almost the same as for cyclopentane, 26.3 kilocalories per mole relative to a linear precursor. When we get up to a five-membered ring, that starts being more reasonable, and there's tons of four-membered rings in organic chemistry, but there's even more five-membered rings. Again, if you were perfectly flat here, you'd have to have an angle that was somewhat different than the tetrahedral angle, and you would have all of the hydrogens eclipsed. So instead, the five-membered rings pucker in predictable ways, and people talk about their conformations, but they're not as easy to understand as are the chair conformations. So let me show you a couple examples of the puckered conformations for cyclopentane. One of them is called an envelope conformation, and that is where atoms 1, 2, 3, and 4 are basically in close to the same plane, and then atom 5 is out of the plane. Why do they call this an envelope conformation? Because it looks like this is the envelope. It's so dumb. This is the stamp. Somebody's address. Do you guys even know how to send letters? I'm sorry. Back when I was a kid, we used to send letters to each other. Anyway, that's why they call it an envelope conformation. And there's another that they call a half chair. And this looks sort of like this. And they have, you can see there are sort of pseudo-axial and pseudo-equatorial positions for the six-membered ring. In the half chair, instead of being just atom 5 out of plane, atoms 4 and 5 are out of plane, and then here's 1, 2, and 3 in the same plane. And we won't worry about the relative energies of these conformations. If you want to get a sense for what it might look like, we can draw it. There we go. So, and let's see if it's gonna, no. So this would be a half chair conformation. It looks like you have atoms 1, 2, and 3 sort of in the same plane. And then atoms 4 and 5 are above and below that plane. This can be important. 5-membered rings are important in nucleoside chemistry. So in all your nucleic acids, you've got 5-membered ring sugars. One of these is an oxygen instead, and sometimes their shapes can be important. There's also a 5-membered ring amino acid called proline, and its shapes and conformations can be important too, so you may encounter that. The strain energy for cyclopentane, let me look at that, is a whole lot less than for cyclobutane. The bond angles, you can do the math, I forget what the equation is, but even if this angle, even if this 5-membered ring were perfectly flat, I think the internal angle would be something like 108 degrees. So it's not that bad. And overall angle strain for cyclopentane is about 6 kilocalories per mole. And then our friend, the 6-membered ring, adopts the familiar chair form that hopefully you're used to drawing now. And in the chair form, all the bond angles can be tetrahedral, 109.5, and so there's 0 ring strain and 0 torsional strain. Yeah, actually, like strain energy 0.1 kcals per mole. So it's almost like the 6-membered ring doesn't mind being a ring at all. It's about the same as in terms of strain as what it would be if it were linear. Feel pretty comfortable on chairs? Do we need to say anything about that? Pretty good. They're just for your edification. Here is a model of an energy surface for the transition between one chair and the other chair. I tell my undergrads that this allows you to have a secret nerd joke by which you can recognize other nerds at social functions and parties. And the question you ask is, what is the opposite of a chair? And the answer is the other chair. Yeah. Yeah, I mean, only chemists laugh at that. Everybody else is like, okay, moving on. So in going from one chair to the other, sometimes undergraduate texts will tell you you go from one chair to a boat and then to the other chair. Actually, that's not true. When going from one chair to another, you take one of the in this case, let's see, take one of the down carbons and start to move it up a little bit. This is called a half chair because everything else is still sort of a chair except for that carbon. Then and that's a high energy transition state because you can see all of these groups are eclipsed with each other and this bond angle is going to have to be distorted. Then you go to something called a twist boat. In the twist boat, the two sort of hydrogens that are the masts or the prow and the stern of your boat are not pointing directly at each other, they're sideways. And then to go to the other chair, you have to have them slip past each other, and that is the actual boat. That's a transition state. You get into the other twist boat, go through the other half chair, and then go to the chair. And I wonder whether Spartan has that. I haven't looked at it, but let's sort of take a look as we're finishing. And we'll talk more there later. Yeah, that looks like the half chair or something. No? I'm not sure. Or the twist boat. I'll look at that and we'll talk more about it next time. All right. Good luck on your exam. Do your best. Don't panic. Don't panic. Take a deep breath. It'll be okay. And if I write a bad test, I can make adjustments. So just relax. Okay, so I wanted to say one more thing about substituted cyclohexanes. A values describe the equilibrium constant, describe the difference in free energy between having a group axial versus equatorial. And you can use it as a measure for how big a group is within some reason. So, as an example, methyl has a value of 1.7. That means the equatorial conformation is 1.7 kcals per mole more stable than the axial conformation. Notice when you add another group beyond the methyl group, when you tack on an additional CH3 to make it ethyl, that doesn't increase the A value much. It does increase the size of the group, but remember, methyl groups can rotate, and so it's easy to get that additional methyl group out of the way, and so the ring doesn't care so much whether it's methyl or ethyl. You start to introduce branching with this isopropyl group, and it gets worse, and then another branch group, and it gets even worse. And the differences here are all about the group you've attached to the ring being able to rotate to get whatever's here out of the way. Another factor that you have to be aware of is bond length, because that can sometimes lead to counterintuitive effects. For example, in terms of atomic radius, iodide is much bigger than bromide, which is bigger than chloride, but the A values don't change a lot. In fact, they may go down a little bit, and this is because carbon iodide bonds are longer than carbon bromide bonds that are longer from carbon chloride bonds. So, even though it's bigger, that's compensated for by the fact that the group is held further away. Remember that the thing you're trying to avoid in an axial conformation are these diaxial interactions. They're sometimes called 1,3 diaxial interactions, and they are worse if the bonds are shorter here. If this group is out further, there's not as much steric clashing. Lastly, things as you start to add more groups, axial conformations become less perfect. So you can see that these two methyl groups that are axial to each other are not perfectly axial, and this is no longer a perfect chair. The chair will try to distort itself to avoid steric problems. Yeah.
So obviously equatorial is more stable than axial, but when it comes to the A value, is that for an equatorial group or for an axial group, or just a combination?
That's difference in free energy between axial versus equatorial. So if you set the equatorial conformation to 0, the axial is this much higher than that. Yep. And for the most part, in OChem, we care about energy differences. So on your computational assignment, there were times where I asked you to talk about the difference between two different conformations, and I said set the lowest energy one equal to 0. That's just because all we care about is the difference. Your computations calculate, I think those numbers represent how much lower in energy your molecule is than all of the atoms and all of the electrons separated and at infinite distance. And generally that's not how we make molecules, so that's not relevant. But the differences are. Some people have done some creative things with cyclohexane rings to measure strengths of non-covalent interactions. As an example, Eric Anslin, who is one of the authors of your text, published this in JAX in the 90s. And he was interested in the strength of hydrogen bonds. And so he took this substituted cyclohexane. The two groups are trans, the two OHs are trans, and he measured the equilibrium constant, or the change in free energy, as you go from a conformation where the isopropyl is equatorial to where it is axial. The interesting thing is, though, that when the isopropyl group is axial, those trans hydroxyls stay trans, but they become equatorial, and that brings them close enough to each other to potentially hydrogen bond. And so he measured this change in folding free energy, and then he used the A values up here to account for how much better it is to have isopropyl equatorial versus axial, how much better it is to have OH's equatorial versus axial. And he assumed that the difference in energy between these two would be related to the A value of the isopropyl group. So it's like, that's like 2.2. And that's uphill in free energy because you're going from equatorial to axial. And then he subtracted 2 times the A value of the OH group because you were going from axial to equatorial. And he reasoned that whatever was left might be the energy of a hydrogen bond. So by measuring this free energy or equilibrium constant and then subtracting this term for the change in A values, he could come up with how much the hydrogen bond was worth. So kind of a cute little study. Of course, hydrogen bond strength varies dramatically as a function of context. If your solvent is water, it's different than if it's a nonpolar solvent. And that's true in the protein folding world as well. Generally, you're thinking of anywhere between 1 to 10 kilocalories per mole. All right. Since this is a physical organic chemistry course, I just have to pay temporary lip service to all of the crazy ring structures that people have made in a desire to understand ring strain. There are a few important principles that are maybe interesting. One is that as you've looked, we have some type of rings where the strain is pretty high. And then we have other types of rings where the strain is pretty low. And maybe we have some other intermediate strain as we go from 9 to 10 to 11. So we've already talked about why ring strain is pretty high in the 3 to 4 region. We've talked about why it gets relieved when you go to 6. Why does it start going up again when you increase the number of atoms? And the reason for that is that there's no nice chair conformation that allows you to have perfect bond angles and no eclipsed interactions. In particular, here is a low energy conformation of cyclodecane, and as you look at it and show the space filling model, you're actually bringing CHs from across the ring and bumping into each other. And that's part of the reason why the ring strain goes up, is simply by trying to keep all the bond angles reasonable, you end up with CHs pointing at each other. This is much worse than, say, the axial protons on a cyclohexane ring, because those are parallel to each other and these are pointing to each other. Would I expect you to predict that this is the case? No. But realize if you're going to be making rings, if you're going to do macrocyclization in your research, you might expect it to be straightforward for rings of this size, sort of from 5 to 8. But you might expect to have some trouble in the sort of 9 to 11 region. And then beyond that, the ring strain doesn't go up a lot, but you've still got the problem of taking two groups that are far away from each other and bringing them together. So making rings is a famous and important part of OChem. I'm actually going to talk a little bit about that in my research talk tomorrow, but be aware of those kinds of things. And when someone makes a really, really large ring successfully, that's impressive. when someone has a reaction that really works to make a ring where there's a lot of strain, that's impressive too. So, because many fields in chemistry were once dominated by probably men who were trying to impress each other, we have a bunch of molecules here that have increasing levels of strain. And the numbers are shown here. This is strain energy relative to non-strained analog compounds.
So these have all been synthesized?
Have all been synthesized, but I don't think many of them are that stable. And so maybe some of these are just estimates. Let's see, what's worth talking about? The trans decalin. This is a 10 carbon system, 2 fused cyclohexane rings, almost no ring strain. I don't know what negative ring strain means. Maybe this means it's even happier than it would otherwise be linear. You go with cis, and that's strained. The reason for that is the cis fused ring system always has to have one axial and one equatorial, whereas the transfused ring system, you can have both ring substituents equatorial. Some of the bicyclic ring systems have interesting amounts of strain. So let's see. Here's a 5-membered ring, and here's 2 5-membered rings fused together, and it's not that much more unstable. One of the interesting things to look at, though, is what happens when you try to bring a double bond near that bridgehead carbon. We won't talk very much about this, but if you ever get into physical organic chemistry, there was a question as to whether there could really be a p orbital there overlapping with this carbon to make a double bond. Let's see. Some of the more exotic ones are cubane and tetrahedrane. And then, let's see, which ones most offend our sensibilities? Maybe this benzene ring with the cyclopropane ring attached to it. That just seems like that bond angle wants to be 120, and now it's forced to be something less than that. Here's an interesting one. You may have learned that you can't have trans double bonds in 6-membered rings. It just doesn't work out. You can't close the ring. The smallest size ring that allows you to have a trans double bond is the octane, cyclooctane. So you can have trans cyclooctene. Here's what it looks like, and it has to twist so that the double bond is sort of lying on its side, and one proton is up and one proton's up and the other is down. So we're looking at the ring, we're looking on the edge, and here's a proton coming towards us, here's one going back in the page. The bond angles are not perfect for a double bond, so you might expect that to be a little bit more reactive than a double bond is. You can see this is not perfectly flat, it's sort of pyramidalized, but you can force it and make it work. The idea of incorporating bonds into rings that would make the ring particularly strained has become really useful in organic chemistry. So, years ago, there was a study about a cycloaddition that was called the Huisgen cycloaddition. And this was a reaction where you took an azide and an alkyne, and I think if you cooked them and let them sort of stare at each other, the reaction really wasn't that efficient, but you could eventually maybe get the following heterocycle, which is called a triazole. Okay. Wasn't that useful back then, but more recently, in the mid 90s, I think, and early 2000s, Barry Sharpless and others found that if you added a copper 1 catalyst, that reaction went really well at room temperature in various solvents. And the nice thing about it is that if you're dealing with biological molecules, they don't naturally have a lot of azides or alkynes, and so you can do some interesting chemistry in the presence of unprotected biological molecules. That will take, so the copper catalyst greatly accelerates the cycloaddition. This is often called the copper catalyzed, this is not like it would make it easier to say, azide alkyne cycloaddition. People often say it's click chemistry. That's a word in chemistry for reactions that are efficient and proceed without interference from other biological functional groups. We call them bio-orthogonal reactions. Sometimes people call this the click reaction. Click chemistry more properly applies to a bunch of reactions that satisfy these criteria of being efficient, easy, and orthogonal to other biological functional groups. Sometimes you'll see people abbreviate this as CUAAC, AC, or something. When I'm writing, I often just abbreviate like that because this is often hard to do. So a lot of people have used this reaction for a lot of different purposes. But one of the things that people have wanted to do is to use this to, in the presence of biological systems. What if you could somehow get a protein to incorporate an azide? And it turns out there are ways to do that. Could you then specifically label a particular protein with some fluorophore or some other useful functional group just by making that group attached to an alkyne, and then you do the azide alkyne cycloaddition. You got the triazole linkage, you've clicked the thing you want onto the protein just at that spot. You can make proteins with new properties. The challenge is that copper 1, there's sort of two challenges. Copper 1 wants to oxidize to copper 2 in air, so you have to do something to keep it reduced. Second, copper tends to be toxic to biology in large amounts. So the challenge was, how do we get this reaction to go faster if you don't use the copper catalyst? Because then you're sort of back to the drawing board of the azide alkyne cycloaddition that doesn't work well. Enter Carolyn Bertozzi, based on work by Wittig, made this cyclooctine ring. Now that's an alkyne in an 8-membered ring. That should be highly strained, because the bond angles want to be linear, but they're constrained to be something different from that. We don't have a representation here of what that ring conformation actually is. But when you bring this strained ring into the presence of an azide, the relief of that ring strain, turning it from turning these carbons from sp hybridized to sp2 with a sort of cis double bond, that strain relief is enough to drive the reaction, and it actually works quite well. So this is called the strain promoted or copper-free azide alkyne cycloaddition. And this isn't the only cyclooctine that's used. There are others as well. But Bertozzi has done this a lot. She's labeled living cells with azides on their surface. She in the classic and maybe most famous experiment, she fed cells carbohydrates that had azido groups on them, and the cells incorporated those carbohydrates into their surface proteins, and then she threw a cyclooctine linked to something else, perhaps a fluorophore, at the molecules, and labeled the surface, and the cells were still alive. And so there's a lot of interesting things you can do with that technology, but that's based on ring strain. Okay, anything else we need to talk about there?
Okay, is it shapeless or sharpless?
Sharpless, yeah. That's Professor K. Barry Sharpless at the Scripps Research Institute. He won a Nobel Prize, I think, in the early 2000s for the asymmetric epoxidation reaction. And there are people who have speculated since then that it might be worth a Nobel Prize. This other reaction might also be worth a Nobel Prize.
Okay, so he was the one.
He was the one that said, "Hey, let's try copper." Yeah. Let's see. And these issues are important in the Savage group. So Paul Savage's group has one of their projects in which they make carbohydrate antigens for various bacteria and viruses. Go ahead.
You can finish for a second. I wish after. So,
Oh.
how do you choose copper? Like, they just random one day
They
say,
just-
hey,
yeah.
I dumped copper in my
Why copper?
Yeah. Like,
I don't know. I suspect there was a rationale, and it probably has to do with copper's other chemistry and whether it was similar or not.
okay.
There's two ways you do research, right? You do research where you think you have a hypothesis and you try it and it either works or doesn't, and then you adjust. And there's also research where you throw the kitchen sink at a problem and just try a bunch of things and then you see what works.
Okay.
A lot of asymmetric, like make enantioselective reactions, in many cases what they do is they have a reaction that works, and then they're like, how do we make it enantioselective? Well, let's try some chiral ligands for this metal. Well, this one doesn't work. How about this one? Well, how many can we buy? Or how many can we make? And let's try them all. So it depends, and I don't know what the story is. But the student or the postdoc who was in Sharpless's lab when this was discovered is named M.G. Finn, and he's now a very famous chemist, and he collaborates with the Savage Lab. The Savage Lab makes these carbohydrate antigens that bacteria make, and they conjugate them to azides or alkynes, and then they send those to M.G. Finn's lab. He has these virus-like particles, which are these sort of nanoparticle-sized things made of proteins, into which he has incorporated azides or alkynes. So they conjugate their carbohydrates onto the surface of this virus-like particle, and then they use that as the basis for a vaccine. And the idea is, could you vaccinate people against various bacterial infections? Could you vaccinate them against viruses that have been difficult? And they've had quite a lot of success there. So this reaction is really quite important. It doesn't work in our lab's hands as well. I think anybody that's tried it will tell you it doesn't work quite as well as the hype says. If you're going to do the copper catalyzed azide alkyne cycloaddition, its efficiency depends a lot on the concentration of copper and alkyne and azide. It depends a lot on the solution. There are times when we've been able to get it to work and times where we haven't, and it can be something of a challenge. I've never done the strain promoted one, so I don't know how easy that is to do. But if you ever decide you want to do that, come talk to somebody in the Savage Lab or one of my grad students, because we can probably save you some time messing around and not getting stuff to work. Okay. So we've dealt mostly with how sterics and strain influence the structure of organic molecules. We now want to talk about how electronic factors can influence molecules. So we're going to start, and I guess we could call this, there's a lot of electronic factors, some of which I think are straightforward to understand. We may not talk a lot about aromaticity because I think you guys already know about it, and I don't know that there's that much we need to say that's extra, so don't forget that. Aromaticity is still important, but we may not spend a lot of time on it. Stereoelectronic effects. These are effects that happen because of the particular orientation of groups relative to each other that introduce some kind of interaction that can change the stability of a molecule. So the first one is called the gauche effect. All right, so here is 1,2-difluoroethane, and I've drawn it as though it would be in the anti-conformation. What reason would I have to believe that the anti-conformation is, when I have the fluoro groups anti to each other, what reason do I have to believe that that might be better than, say, having the fluoro groups gauche to each other? For butane anyway, why did you say anti was better than gauche? Sorry? Anti has lower energy, good, and why is that? More stable because sterics. Yeah, because of steric hindrance, it minimizes the steric hindrance between the two methyl groups. Now, fluoro groups are actually quite a bit smaller than methyl groups, but they're still a little bigger than hydrogen. So you might expect that the anti-conformation might be better than the gauche conformation because the anti-conformation minimizes steric hindrance. However, dun dun dun, for this 1,2-difluoroethane, the gauche conformation is actually more stable. So there's a fun rule of thumb in organic chemistry that people say if it's not sterics, it's got to be electronics. So if you can't explain an effect based on the size of a group, you want to start thinking about what might be happening with the electrons. Okay, so let's think about bonding in this molecule. And in doing so, we're going to think about a hybrid between valence bond theory and molecular orbital theory. That is, we're still going to think about bonds as being localized between two atoms, even though we know we don't have to. But we'll keep in mind the idea of there being both bonding and anti-bonding orbitals, more stable. And we were thinking about the answer why. And in order to do this, we need to review a concept from valence bond theory, but we're also going to consider MO theory as well. We're going to use a hybrid approach. And we're going to talk about what are called sometimes donor-acceptor interactions. That's interactions between a filled orbital in the molecule at one location and an empty orbital in another location. Sometimes it's called hyperconjugation. Of course, in pure MO theory, there's no need for any such thing because all of the orbitals are delocalized anyway. MO theory sort of accounts for that in the basic math of how it works. But it's helpful in sort of thinking about these issues to take a hybrid approach. So when we think of, excuse me, 1,2-difluoroethane, we're going to consider the sigma bonds as being two electrons shared between two atoms. Okay. And now let's consider where we would expect in energy the sigma bonding orbitals to be versus the sigma star anti-bonding orbitals to be in energy, just relative to each other. All right. We've got a few different kinds of bonds. We've got 4 carbon-hydrogen bonds. And then we have 2, I don't know why I can't count. We have 2 carbon-fluorine sigma bonds. Also, we have a carbon-carbon bond, but that's the one we're not involving that at all in this process other than it's the bond we're rotating around. And of course, if we have 4 carbon-hydrogen sigma bonding orbitals, we should have 4 carbon-hydrogen sigma star anti-bonding orbitals and 2 carbon-fluorine sigma star anti-bonding orbitals. Just for the sake of our discussion, if we're thinking about a carbon-hydrogen bonding orbital, that would presumably come from an sp3 type orbital on carbon overlapping with a 1s orbital from hydrogen. And if this is carbon and this is the hydrogen, that orbital is going to look something like this. Similarly, if we were to overlap an sp3 orbital on carbon, probably with the corresponding p orbital on fluorine, we would expect a bonding orbital that looked like this, with a lobe between the two nuclei and then lobes on either side with the other phase. Antibonding orbitals, so those would be sigmas. Antibonding orbitals would presumably look like this. For carbon and hydrogen, you would have a node in between the two nuclei, and then a smaller lobe here and a larger lobe there, and then a lobe there, and we'll just use shading. This is the minus combination. Similarly, the sigma star for the carbon-fluorine bond would look like this. Large lobe in this direction, small lobe here, node there, small lobe there, large lobe in this direction. So what I've drawn for you here are localized bonding and antibonding orbitals. This is what you would get if you did Gaussian and you clicked the box that said NBO analysis. This is a version of molecular orbital theory where you mathematically transform the molecular orbitals into localized orbitals, and the way of describing the molecules are fully equivalent. Any questions about what sigma and sigma stars look like? Okay. Now, let's talk about their relative energies. Okay, and we were doing this just as class ended last time. Carbon-hydrogen bonds are generally worth, their bond association energies are about 104 kilocalories per mole. In contrast, carbon-fluorine bonds are worth about 109 kilocalories per mole. So, if you have to rank in energy where sigma bonding orbital should be, where is the carbon-fluorine bonding orbital relative to the carbon-hydrogen bonding orbital? Should be lower, right? And you can tell that just from the bond energy. But if we wanted to rationalize that, what we would say is that when you make a bonding orbital between an sp3 hybridized orbital on carbon and a 1s orbital on hydrogen, you get the sigma bonding orbital here. But fluorine starts out at a lower energy level. The 2p orbital on fluorine is actually lower in energy than on the orbital on hydrogen. Fluorine's more electronegative than hydrogen. So this means that because you start out at a lower point, the bonding orbital you make is going to be lower. Okay? Now, how about the energy difference between the antibonding orbitals, sigma star for carbon-hydrogen versus sigma star for carbon-fluorine? What do you expect there? Do you remember what we learned in, what was it, chapter 14 or chapter 1? When two orbitals are close in energy, the amount of stabilization relative to the starting orbital is higher, and the amount of destabilization relative to the starting orbitals is also higher. Whereas when two orbitals are different in energy, the amount you go down relative to the starting orbital is smaller. Now, you started out lower to begin with, so the orbital that you make is still lower in energy than the carbon-hydrogen bond. But what this means is the sigma star antibonding orbital for the carbon-fluorine bond isn't going to be as high above carbon as the sigma CH antibonding orbital is. In other words, another way of thinking about this is just to start with the carbon-hydrogen sigma and sigma stars, and then say, let's switch hydrogen to fluorine. Fluorine's more electronegative than hydrogen, so that should pull both orbitals downward. That's an alternative way of thinking about that. It's called perturbation theory. Yeah.
So before we had learned that the anti-bonding orbital is always more destabilized than the bonding is stabilized.
Yes.
Does that not apply here then?
You're exactly right, and that just means that my drawing is dumb because I didn't do it to scale.
Okay, that's
So,
fine.
shall we try again?
No, it's okay. I just
Yeah, so here would be an sp3 on carbon, and let's say a 1s on hydrogen. So here we've gone down in stability by about 3 units. Here we've gone up about 4 in our drawing. This would be the carbon hydrogen sigma star. This would be the carbon hydrogen sigma. Let's say fluorine starts out here, and I don't, relatively, I'm not sure how that would go. Let's suppose we only go down 2 units for fluorine instead of 3. Because the difference in energy to begin with is larger. But by virtue of the fact that fluorine starts out lower, even though we're only stabilizing by about 2 units, we're still lower in energy than the carbon hydrogen sigma star. Then let's say the anti-bonding orbital will go up by 2.5 or 3 units. That's still larger than the little red line here, but it doesn't put us as high above carbon as we were for the carbon hydrogen orbital. I think that's maybe self-consistent. But it's also fine if you don't want to go through all of that to just say, okay, well, here's where carbon hydrogen sigma and sigma star are. Replacing hydrogen with fluorine, which is more electronegative, pulls both of those down in energy. So what that means is that my highest, and of course the carbon hydrogen bonding orbitals would be filled, the anti-bonding orbitals would be unfilled, but my highest energy bonding orbital is going to be sigma CH, but my lowest energy anti-bonding orbital is going to be the carbon fluorine sigma star. Now, how does that play out in the conformations of this molecule? One of the things that we didn't talk about when we were discussing staggered versus eclipsed, and in particular when you were doing those MO calculations, is that the staggered conformation allows a sigma bonding orbital that is filled on one of the carbons to overlap with a sigma star anti-bonding orbital on the adjacent carbon. Now you can go through this analysis using group orbitals and you'll get the same answer, but this is a useful way of thinking about it. Imagine you have a filled orbital in the same molecule as an adjacent empty orbital, sigma star carbon hydrogen bond. The filled carbon hydrogen bond can donate electron density into the anti-bonding orbital. That's called hyperconjugation. You can think of this as though there was some orbital mixing going on. So imagine having a carbon hydrogen bonding orbital mixing with a carbon hydrogen sigma star anti-bonding orbital. The bonding orbital is going to go down in energy just a little bit. The anti-bonding orbital is going to go up in energy just a little bit, but we don't care because the electrons delocalize a little bit and they go down in energy. So That's a stabilizing effect. If you can't see how these line up, consider drawing a Newman projection from this angle and convince yourself that this bonding orbital lines up with the large lobe on the carbon-hydrogen antibonding orbital on the adjacent carbon. So that's, in addition to sterics, that's one factor, one reason why staggered is more favorable than eclipsed. Now, let's replace both of those hydrogens with fluorines, shall we? And see what happens. And see if there's an alternative, better arrangement. So, imagine we start in the anti-conformation, which I've already told you is not as stable. Let's draw the carbon-fluorine sigma bonding orbital. And we'll do this with sort of a large lobe here, smaller lobes on the outside, and have this be pink. Nodes at the nuclei, wave function change in sign. Colors simply represent opposite wave function signs. Let's draw the antibonding orbital for the carbon-fluorine bond. As we would expect, there would be a node in the middle, small lobe here, large lobe there, small lobe here, large lobe there. We can fill in the colors representing wave function sign. Here you have a filled carbon-fluorine bonding orbital and an empty carbon-fluorine sigma star. And you could still get donation of electron density from the carbon-fluorine sigma to the carbon-fluorine sigma star. But let's consider an alternative. What if we keep everything the same, only we rotate around the bond between carbons 1 and 2, such that instead of having a fluoro anti to the other fluoro, we now have a hydrogen. Okay? In that conformation, the empty antibonding orbital that would line up with this filled carbon-fluorine sigma bonding orbital would no longer be the carbon-fluorine sigma star. Rather, it would be the carbon-hydrogen sigma star. Now, based on what we've talked about, which of these arrangements is better? Is it better for the carbon-fluorine sigma bonding orbital to overlap with carbon-fluorine sigma star or carbon-hydrogen sigma star? What do you think?
Probably carbon-hydrogen.
Carbon-hydrogen, right? Okay, can you explain why? Because I told you it was more stable. Good.
Maybe because of hyperconjugation, as you explained earlier.
It's because of hyperconjugation, but that's going on in both of these cases. So do you have any reason to believe this would be better than this? This hyperconjugation would be better than that one? Go ahead.
There's less nodes.
Okay, fewer nodes. I will agree that the hydrogen doesn't have a node there. Does that have a major effect? I don't think that's the major thing that's going on. Let's just compare two options. Carbon-fluorine sigma bonding orbital gonna mix with either a carbon. Did I go about this the wrong way? Oh, I am thinking of this backwards, aren't I? Okay, I need to back up just a little bit because where we're going, we could come around to the right answer. But the real deal has to do not with, the reason for this has to do not with which orbital the carbon-fluorine bond is donating into, but rather with, why is this not working in my head? Just a second.
I think from the orbital diagram we drew, the carbon fluorine is closer to the carbon fluorine sigma bond is closer to carbon fluorine antibonding orbital.
Okay. So let's frame the discussion this way. I'm going to erase what I've drawn over here on the right because that wasn't the right comparison to make to help you see the stability difference. Of the two empty orbitals that we have, which is going to be the best acceptor? The lower energy one, right? The carbon, fluorine, sigma star. Of the filled orbitals, which is going to be the best donor? Carbon, hydrogen, right? So what I really should have showed you is compared the situation. Here is our best carbon, fluorine, sigma star. This is our best acceptor. What I should have compared is having our carbon, fluorine versus carbon, hydrogen donating into that best acceptor. So I'm sorry for that oversight. Let's leave the carbon, fluorine bond over here in that place, and let's continue to draw that carbon, fluorine, sigma star right there. But instead of having the carbon-fluorine bond being the donor, let's now have the carbon-hydrogen bond being the donor. And what I hope you'll see is that having the carbon-hydrogen bond anti to the carbon-fluorine bond lines up our best, Joshua, our best acceptor with our best donor. Okay? Do you see that? It's only when the fluorine is anti to a hydrogen that you line up your highest energy bonding orbital, which is the carbon-hydrogen one, with your lowest energy anti-bonding orbital. And it just so happens that when you do that, doesn't matter whether it's this hydrogen or we rotate that hydrogen, the fluorines are going to be gauche to each other. Okay? That's called the gauche effect. When you have electronegative heteroatoms on adjacent carbons, they might prefer to be, there'll be a preference for them to be gauche with each other. Yeah?
Okay, so I was doing a question with my organic students, and we were talking about basically this, and they were drawing Newman projections with it, and we decided that the more stable was the gauche. That was the major product, and they said it was because of the dipole moment.
Okay, because of the dipole moment.
Between the two fluorines, and the other one would have a net dipole of 0, and the compound has a net dipole, I think it was like 2.5.
Right, so...
is that just a result of this, basically?
Well, so the way of reasoning this out was that over here, the dipole would equal 0. Over here, there would be a net dipole. Is that right?
Yeah.
Okay, so my question back is, well, which of those is more favorable, and how can you tell?
Yes, that's what I'm asking.
Okay.
I'm saying, do we know that this one, like the question was like, this is more favorable because it has a net dipole moment. Is it really more favorable because of this effect that we're learning right now?
I think so. I think so. The dipole thing should be a consequence. Now, we're just imagining these molecules by themselves, right?
Yeah.
I would think that alone in the gas phase, probably having a zero dipole is maybe better. But can you think of a situation where having a net dipole might be better? What if you're not in a vacuum? What kind of solvent might promote having a dipole? Polar, right? If the solvent is polar and has dipoles, then maybe the conformation that has a dipole is more favorable. So I think it's context dependent.
Okay.
But all other things being equal, there's some bias in favor of gauche. And I think you're right. I think the net dipole thing may be a consequence of this effect, not the reason for it.
Okay.
Yeah. Others?
Oh, I have another
Yeah.
question, sorry. I guess I was just kind of confused about why we're comparing, because usually we just compare like filled to filled and antibonding to antibonding.
Yeah.
Are we just comparing the filled to empty because of this difference where our highest energy bonding is the sigma CH and our lowest antibonding is the sigma
Right.
CF?
So the reason we're doing that, if we were doing MO theory, what we would have done is we would have taken the two basically methyl groups, and we would have distorted them by substituting one for fluorine, and we would have had to see how that changed the methyl groups. Then we would have brought the two methyl groups together, and we would have considered whether it would have been better to have the fluoros gauche or anti to each other. And we would have seen that in some cases there's better orbital overlap, or there's more stabilization because of two orbitals mixing at the same energy versus different energies. And that would have led us to this conclusion. That's difficult to do in your head. So treating each bond as an individual sigma bonding orbital with an associated sigma star, but then considering the ability of filled and empty orbitals to mix, takes valence bond theory and mixes in a little bit of delocalization so you can get to the answers of MO theory. Yeah.